Hello everyone, this is Changjie Wang from KTH Royal Institute of Technology. Today I'm going to present our paper, From Scientific Text to Verifiable Code, Automating the Process with Transformer. This is a joint work with Mariano and Marco. Throughout history, humans have continually developed advanced algorithms to solve complex problems and use this knowledge to build a software that runs in modern-day systems. However, despite the vast body of algorithm knowledge, only a small fraction of today's code in system has been formally verified. The reason for this lies in the inherent complexity and challenges in formal verification process. This complexity arises from several factors. First, it requires familiarity with specialized formal language, which has their own syntax and semantics. Second, the formal verification process operate at extremely low level, and every step, even those that are obvious to human, must be explicitly verified. Third, verifiers attempt to aid this process by using heuristics, but it could result in something we commonly know as brittleness. Finally, even if one could skip proving low-level lemmas, translating proof from human language into high-level verifiable code remains time-consuming. This makes us to think whether there exists a tool that can simplify the process. That's what we might get from a transformer. And typically, a transformer will take tasks explained in human language and output some syntax, code, and configuration. LLMs are the most widely used transformers these days. And there are many LLM-based code generators, however, they only focus on generating code in common programming language. Of course, the code generated by this LLM could be wrong and the developers always need to check it manually. This makes us think that whether there exists a tool that can generate verification code based on human written proof. In an ideal case, we want to have a system, we call it promises here, that can take input of an existing program and the written proof and directly verify the program for us. However, opportunities always come with challenges. Here is the example of Daphne, which is a formal verification language. Assume that we have a program to calculate the sum of degree in a graph. But actually it only returns 2 times the number of edges of the graph. Now there is a paper written lemma called handshake lemma to prove that the sum of degrees actually equals to 2 times the number of edges. And we want to formally verify this code in Daphne, and the expected code is on the right side. Looking at this code, first we need to transfer the textual proof into Daphne. For example, here we create a handshake lemma and call it from the original function, and we try to prove it based on the textual proof. Second, after we add all the statements from the textual proof, we can notice that we still need to prove some low-level details. For example, here, x, which is the number of edge vertex pairs, is equal to the sum of degree. And x is also equal to the 2 times of the number of edges. These attribute to human, but may need to be explicitly proved in Daphne. And to prove them, we should also provide more low-level details by adding assertions, invariants, or extra lemmas. Therefore, we propose using transformer to verify the code in the same way, and here is a feasible prototype. First, we use transformer to do the translation of a high-level proof to get the main code and the main lemmas. Transformers are good at translation that are roughly one-to-one, making them well suited for this task. Then we create a tree data structure to deal with other low-level details in a more fine-grained way, and we use transformer in each low-level step to generate proofs that are lacking textual equivalence, typically because their solutions are obvious to human. We conduct a preliminary evaluation to the approach, and to do so, we create 3 simple algorithms to be verified, each of them with a lemma to be proved together with a proof in natural language. We use Cloud Solid 3.5 as our model, and we compared our prototype promises with a baseline approach which simply uses zero-shot prompting with feedback of Daphne output. Promise successfully generate complete and verified code in Daphne with a high success rate. Of course, there are still some challenges, for example, who verify the correctness of the input formal specification, which means we are verifying the property that we want to verify, and how do we reference external theorems of proof which has already been defined somewhere else, and how far can we go in proving theorems without a textual proof. This remains our future work. Thank you for listening. We are hiring PhD students working on this topic as well, and we are open to collaboration.